This is a math project for Calculus for the Biological Sciences by Maxwell Hoffel, Thomas Flick, and Adam Grazzini. We are doing problem 4, animal behavior. Before we begin, I'm going to give a brief description of the problem. The first question we have to answer is, do canine species have the natural ability to optimize the time and distance needed to travel from point A on land to point B in water? To explain a little more, imagine a situation where a dog named Lassie happens upon a drowning person offshore. Lassie needs to save them in the least amount of time possible. 3 hypotheses were formulated in the context of the problem and are presented here below. If Lassie jumps into the water and begins to swim toward the drowning person in order to minimize the distance traveled, then this will minimize the time taken to reach the drowning person. Second, if Lassie runs down the beach until she is able to turn at a right angle and swim directly to the person, then this will minimize the time taken to reach the drowning person. Finally, if Lassie runs a certain distance along the shore, enters the ocean at a specified point, and swims diagonally to the drowning person, then this will minimize the time taken to reach the drowning person. Here's a picture that gives a better description. In the bottom right corner, you see Lassie and her friend. In the top right corner in the ocean, you see the drowning person. Part A, or Hypothesis 1, Lassie swims directly to the drowning person. Hypothesis 2, Lassie runs down the shoreline to the drowning person, makes a right angle, and swims to the drowning person. Or Hypothesis 3, Lassie runs down about halfway through the shoreline and swims diagonally to the person. To find a solution to the problem, we had to develop 4 different methods. In part 1, we developed an equation using the previous diagram where R represents the rate at which Lassie can run, S represents the rate at which Lassie can swim, T of Y represents the time it takes Lassie to arrive at the point in which the person is drowning, D represents the point in which Lassie jumps into the water, and Y represents the distance in meters between point D and point C. This equation will be used to find the value of Y that minimizes T of Y, and then we will provide an interpretation of the resulting equation in the cases where R is less than S, R is greater than S, and R is equal to S. Later on in Part 2, we use the equation from Part 1 and the running and swimming time data from the study by Timothy Pennings to determine the interrelation between the distances Y and X. If you are looking for more clarification, I'll go over the diagram. In Part 3, we use the results from Part 2 and provide an argument regarding Elvis's innate ability to do calculus using the 35 pieces of data collected by Timothy Pennington. Pennington collected data by throwing a tennis ball in the water for Elvis and recording X, the distance from the ball to shore, and Y, the distance between D and C. The relationship between X and Y from Pennington's study will be plotted on a graph and analyzed in the context of the optimized X and Y relationship found in Part 2. To show whether dogs have the innate ability to optimize the time it takes to retrieve an object from the water. Finally, in Part 4, we discuss limitations and assumptions used in our methods and analysis. Let's begin. Part 1, from the diagram we created, a total time equation listed below. This is our first equation. T of Y is equal to Z minus Y divided by R plus the square root of X squared plus Y squared divided by S, where the square root of X squared plus Y squared represents the distance Lassie swims in the water, and Z minus Y represents the distance Lassie runs on land. Also, since time is equal to distance rate, we divided each distance equation by the respective rate variables R and S, giving the time equation. Then the first derivative of this equation was found in the context of a situation where the distances Z and X remain constant. Just as Lassie's running and swimming rates, thus the time it takes Lassie to reach a drowning person would only change as the distance Y changed. This operation gave equation 2, listed below. T prime of Y is equal to Y divided by S square root of X squared plus Y squared, minus 1 divided by r. To continue on part 1, the given derivative was set equal to 0 in order to find the critical points. This operation gave us equation number 3. Y is equal to s times x divided by the square root of r squared minus s squared. The previous equation can be used to find a value of y that will minimize the original time function. When r is less than x, the denominator of the equation 3 will be the square root of the negative number, thus giving an imaginary number for the distance y. Obviously, this does not make sense. When r is greater than s, the denominator of the equation 3 will be the square root of the positive number, thus giving a positive value for distance y. This makes more sense. To finish up on part 1, when r is equal to s, the denominator of equation 3 will be 0, and it is impossible to divide this by 0. Again, this doesn't make much sense. Therefore, the running speed must be greater than the swimming speed in order to utilize the above equation to calculate the distance y Lassie should run in order to rescue the drowning person, in order to minimize the amount of time taken. Moving on to part 2. On the right, we have an equation that Timothy Pennington collected, running times for 20 meters in seconds, and then swimming times for 10 meters, in seconds. Then we took the average running and swimming time that were determined from the data in Table 1. The distance for which the times were recorded was then divided by the average of the running or swimming time to give a rate in meters per second. The running rate r was found to be 6.35 meters per second, and the swimming rate s was determined to be 0.872 meters per second. These values were then plugged into the equation and were found when the derivative was set equal to 0. That was done in part 1. Part 2 continued. This operation gave equation number 4. T prime of y is equal to 1.1464y divided by the square root of x squared plus y squared minus 0.1575. Setting this equation equal to 0 in order to find the value of y that minimizes the time function gives equation number 5. Y is equal to 0.139 times x. The previous equation models the relationship between the distances of x and y when time is minimized. Analysis of part 2. The equation found allows the determination of the point at which the dog should enter the water. Given distance x, and assuming said dog's running and swimming rates are consistent with those used in our analysis. Equation 5, where y is equal to 0.139x, indicates that dogs should run almost the entire length of distance c, the beach, in order to get to point B in least amount of time, because the equation shows that the y distance is approximately 1/10 the distance x. And if you want more clarification with that, you can go back to look at the picture diagram. Part 3. This is table number 2. This is data from Timothy Pennington's experiment with Elvis, his dog. I believe it was conducted in 2003. I'm not going to go over all the data points, but as you can see, he ran the experiment multiple times, and this is the data he collected. Part 3 continued. This is figure 1. It's the relationship between the distances x and y in the Pennington experiment, and this is a graph of the data he collected. Continuing part 3. The optimized relationship between distances x and y presented in part 2 was found to be y is equal to 0.139x. When this is compared to the trend line of the data presented in the Pennington experiment, y is equal to 0.195x minus 0.3102, it can be seen that the linear equations are fairly similar, accounting for the fact that the r-squared value for the Pennington trend line is 0.278, which indicates that the trend line does not fit the data well. Finally, part 4, our discussion. Through the analysis and mathematical models presented in parts 1, 2, and 3, we postulate that dogs have an innate ability to optimize the time it takes to retrieve something from the water, such as a drowning person. However, in the data presented from the Pennington experiment, it appears that Ellis lost his ability to optimize the time taken as the object's distance from the shore was increased. This is especially apparent when the perpendicular distance of the object from shore was over roughly 12 meters. The limitations of this analysis include data from only one member of a single species of dog was available, and the small sample size of the data points presented in the Pennington experiment. Assumptions made in the equation formulation include time is equal to distance divided by the rate, and the running rate of the dogs is greater than their swimming rate. See the document titled Derivation Operations as presented in the Animal Behavior presentation to observe the math behind the equations and analysis presented. And I believe that is it. Thank you.